Hi, folks. Today we're going to tie all of our factoring skills and strategies together to learn how to factor polynomials completely. There is one more skill we need to learn before we can factor polynomials completely. We need to learn how to factor by grouping. And factoring by grouping is when you take a polynomial and with four terms, and you're going to group the polynomial into pairs and factor the greatest common factor out of each pair, and then factor out the common binomial factor. That's a whole lot of words. Let's look at what we mean to make sense of this. So we here are given a polynomial with four terms, and we haven't learned how to do this yet. We've only learned how to factor out trinomials, but we're going to learn a strategy here that works for longer polynomials. We're going to group these into pairs that have common factors. So here, there's no common factor to the coefficient out front, but x cubed and x squared, those have a common factor of x squared. And looking here, 2 and 6 share a common factor of 2. So I'm going to group them together like this. And I'm going to factor the greatest common factor out of each pair. So we said that x squared can be factored out of this pair of terms. And if I divide away the x squared, I'm left with x plus 3 inside parentheses. Let's look over here. I already said that 2 is a common factor for 2x and 6, so I factor out the 2. What do I leave behind once I divide out that 2 value? I'm left with an x and a 3 inside parentheses. Now, when I do this, notice what I have here. I have a common x plus 3 in both halves of this expression. Because I have that common factor in both halves of the expression, this is my common binomial factor. I'm going to factor that out and write this as one big multiplication problem. So I've got x plus 3 as my common factor. And now I'm combining this term with this term, x squared plus 2, for my one big multiplication problem. Of course, you have to have a pretty special polynomial to be able to do this, but the ones that we give you do generally work out this way in Algebra 1. So look at what we did at each step. First, we grouped our pairs of terms, found a common factor to pull out from each group of terms, and then looked for a common polynomial term that I could factor out again to write as one big multiplication problem. Let's look at another example. Sometimes our polynomials aren't written in a way that's helpful for us seeing the terms, like x squared plus y. That's not helpful. Those don't share a common term. So I don't want to group those together. But I could put the y with the xy term, and I could put the x with the x squared term. So if I rewrite this as x squared plus x plus y plus xy, then this grouping makes a little bit more sense, because here for the first pairing, I have a common term of x. So if I divide x from both of those terms, I'm left with x plus 1 inside parentheses. And over here, my two terms have y in common. So if I pull out the y factor, I'm left behind with the 1 plus x as my inside parentheses. So I factored out the first half of the equation, I factored the second half of the equation, and now I look for any common terms. And if I find common terms, then I can write the whole polynomial as one big multiplication problem, because my 1 plus x goes in parentheses. Then I'm left with x plus y. also in parentheses, and I am left with one big multiplication problem. As always, if you're not sure you've done it correctly, you can always use FOIL. You can always use the distributive property to take your multiplication problem and put it into standard form and check to make sure that your factorization was correct. Next thing we're going to learn how to do is how to factor polynomials completely. So let's look at what it means to factor completely. First, we need to know what unfactorable polynomials are. And unfactorable polynomials cannot be written as a multiplication problem of simpler polynomials, at least not with integer coefficients. We kind of want whole numbers here. They can be positive, they can be negative, they can be zero, but they need to be integers, not fractions, not decimals. So if something's completely factored, that means the polynomial has been written as a product of unfactorable polynomials. They can't be broken down any further into any simpler multiplication problems. There are going to be 4 strategies for factoring completely. First, you're going to factor out the GCF. Factoring out the GCF is the most important first step because sometimes it looks like you've got a polynomial with a leading coefficient of something that isn't 1, and then just by factoring out the greatest common factor, you make the polynomial much simpler and much easier to factor. Next, you look for those special patterns, a difference of 2 squares or perfect square trinomial, because if you can spot a special pattern, that makes the factoring much faster. Next, you just do normal factoring. This is what we learned in a couple topics ago, just trying a bunch of different factors, seeing which values kind of add up to this center term correctly. And lastly, you can try this strategy that we've just learned about. If you've got a polynomial with 4 terms, a tetranomial, you can factor it by grouping. So let's look at an example. Here we've got a 3-term polynomial. So I'm not going to try the grouping thing. The grouping is 4 terms. And also I'm going to go in order of the steps we just checked. So let's check for greatest common factor first, because right now I see a lead coefficient here and that seems hard to factor. But oh, look, also this is x cubed, x squared, and x. So there's definitely a common factor of at least x here. So I'm going to factor this out. Let's see. Also, 3, 6, and 18 are all divisible by 3. So I can pull out the 3x term. And then if I take each term in this expression and divide away 3x, well, 3 divided by 3 is 1. And x cubed divided by x is just x squared. Then for my next term, 6 divided by 3 is 2, and x squared divided by x is just x. Then I subtract for the final term, and 18 divided by 3 is 6, and x divided by x is just 1, so I leave that as is. So I've pulled out the 3x as a greatest common factor of the 3 terms, and now I'm left with a much simpler, easier to factor polynomial inside the parentheses. So let's focus on this portion inside parentheses now. So I'm going to make a little table of possible values. I've got factors here and what they add up to. So I could have positive 1 with negative 6. I could have negative 1 with positive 6. What other factors of 6 are there? There could be 2. I could have positive 2 with negative 3, or I could have negative 2 with positive 3. And now that I've reached numbers that are just 1 away from each other, I know that I've listed all the possible factors of 6, or negative 6, I should say. And now when I add these together, I get sum totals of negative 5 or positive 5 or negative 1 or positive 1. None of these add up to 2. So there is no way to factor this second this polynomial inside parentheses using integer coefficients. This is unfactorable. So I have already factored this as much as possible. This is as simple as I can go. Um, and that is my final answer. The only way you can be sure whether this is factorable is if you actually look at every possible combination of factors. In a later chapter, we'll learn another strategy of kind of how to deal with unfactorable uh, polynomials. But here, because I listed all the factors and I checked all the possible sums, I know that this is unfactorable with whole number coefficients. All right, let's look at one that maybe we can do a little bit more with. Here, 7x to the fourth minus 28x squared. Once again, I've got a leading coefficient, which I'd like to get rid of if possible, perhaps by pulling out a greatest common factor. So let's try that. Let's see, 7 and 28. If I pull a 7 out of parentheses, 7 divided by 7 is 1. Negative 28 divided by 7 is negative 4. So that's kind of what happens when I pull out that common factor of 7 from the coefficients. Let's look at the variables now. I've got x to the fourth and x squared. I choose the variable with the smaller exponent, pull that out. What's x to the fourth divided by x squared? That leaves me with x squared. What's x squared divided by x squared? The x's cancel out. Any number divided by itself is 1, so there are no x's left in this second term inside parentheses. All right, I've pulled out that greatest common factor, and I look inside parentheses, and this two-term polynomial kind of looks familiar to me. This looks like I have a squared value minus a squared value. And when I see that difference of two squares pattern, then I know how to factor that. I'm going to do something here inside parentheses. I'm going to rewrite this as 7x squared times x plus 2 times x minus 2. Because that difference of squares pattern is factored in that standard way. A plus b times a minus b. This is my a value, this is my b value, and I did a plus b times a minus b. All right, I've really only gotten to step 2 so far here, so maybe we can do another one where we get further along with the steps. How about 2x cubed plus 8x squared equals 10x? Okay, this time I have an equation here. I have an equation that I want to solve, and I'm going to solve it by factoring. Because once I factor, then I can use the zero product property rule to write the polynomial as a multiplication problem and solve for the variable. So first, in order to do this, I need my polynomial to be equal to 0. This polynomial is not equal to 0, so I'm going to have to subtract 10x from both sides of the equation. So I'll have 2x cubed plus 8x squared minus 10x equals 0. I just subtracted 10x from both sides of the equation. Now that I've got my complete polynomial all on one side of the equation and the other side of the equation is equal to 0, I can work on factoring it. Before I factor, I check to see if I've got any fractions because we want to have whole number factors and not fractions or decimals, but I don't have any fractions here. That's fine. So now I'm going to work on factoring the polynomial. I want my polynomial to be written as a multiplication problem, and I'm going to follow those 4 steps. First, we'll pull out a greatest common factor, if there are any. For sure, there's a greatest common factor because all of my coefficients are even. So at the very least, I can factor out a 2. I also notice that all my terms have x in them. So we should be able to factor out an x because my smallest exponent here is x to the first. So I'm going to pull out a 2 and an x. What am I left inside parentheses once I kind of divide away doing the reverse distributive property, dividing away the 2x from each part of the polynomial? 2x cubed, well, the 2 divided by 2 is just 1, so I'm left with a coefficient of 1 here, which I'm not going to write down because I'm going to have an x term as well. X cubed divided by x is x squared is my first term. So this is 1x squared, but we don't typically write down that 1 value. 8 divided by 2 is 4, and x squared divided by x is x, so that's what I'm left behind with. And lastly, I have negative 10 divided by 2 is negative 5, and x divided by x is just 1, so I don't write any x term there at all. So I have pulled out the greatest common factor of the polynomial. And so I have a simpler polynomial inside parentheses. And this is nice because now I do not have a lead coefficient here. My lead coefficient is just 1. It's not a value other than 1. This is going to make it easier to factor. I look at this pattern and I do not see any special patterns here. Although my first term is a perfect square, my last term is not a perfect square. So there are no special difference of squares pattern or perfect square trinomial. So now I just go back to factoring the old-fashioned way. I think about the factors of 5, or I'm sorry, negative 5, and then what they sum up to. So I'll make a complete list here so that I don't miss anything because maybe this is unfactorable. I don't know. I'll do 1 with negative 5 and negative 1 with 5. So just switching around where my negatives are. Because the 5 here is negative, my factors must have opposite signs. One is positive, one is negative. Actually, I can stop with my factor list right now because I see that 1 plus negative 5 is negative 4, and negative 1 plus 5 is positive 4, and that is, in fact, what my center term is. So I still have my 2x as my first part of the multiplication problem, but now we've decided that these are the correct factors. So I'll have x minus 1 as one of my parts of the multiplication problem, and x plus 5 as the final part of my multiplication problem. X minus 1 cannot be further factored. X plus 5 cannot be further factored. So I have now written this as a multiplication problem where all of my factors are unfactorable. There's no further factoring to do here. Therefore, now this equation is ready to be solved. I just set each part equal to 0. So 2x could be 0, or x minus 1 could be 0, or x plus 5 could be 0. And I solve for x. Here I divide both sides by 2, and I get that x equals 0. Here I add 1 to both sides of the equation, and I get x equals positive 1. Here I subtract 5 from both sides of the equation, and I get that x equals negative 5. So those are my roots of this polynomial. And I have solved this polynomial equation. Let's look at a real world problem here. Here we've got some sort of equipment that is in the shape of a rectangular prism. That basically just means it's box shaped, which means the volume is length times width times height. And we say that the volume is 72 cubic meters, and that equals the length is x, the width is x minus 1, and the height is x plus 9. And then it says find the dimensions of the piece of equipment. Okay, so I want to solve for x so that I can find the dimensions of this piece of equipment. But in order to solve for x, in order to solve a polynomial, I need to have my polynomial set equal to 0. I can't solve it unless it's equal to 0. So what I need to do is I need to multiply out this multiplication problem, I need to use the distributive property so that then I have a standard form polynomial. So I can subtract 72 from both sides of the equation. Because right now, subtracting 72 doesn't help me yet. I don't have any like terms on the right-hand side of the equation that I can combine it with. So let's do the multiplication problem first. Let's just do FOIL on these two terms that are in parentheses, and then we'll worry about the x later in the next step. So if I have x times x, that's x squared. X times 9 is 9x. Negative 1 times x is negative 1x. And negative 1 times 9 is negative 9. This could be a little bit further simplified here. I can combine those like terms here. So I've got x times x squared plus 8x minus 9. And now I can distribute that x term onto by multiplying everything inside the parentheses. And I have x cubed times, plus 8x squared minus 9x. Okay, so up to this point, I haven't kind of written the 72 down here, but all of these are equal to 72. Now I'm ready to subtract 72 from both sides of the equation so that I set my equation equal to 0. So 0 equals x cubed plus 8x squared minus 9x minus 72. All right. As soon as you get given a polynomial with 4 terms, you should think about this factoring by grouping strategy that we started this lesson with. Well, the very first thing you should do is look for a greatest common factor. But because we start with x cubed, but our last term does not have any x in it at all, so I can't factor out x. And my first term doesn't have a coefficient, so there's not a greatest common factor that I can pull out of the whole polynomial. So instead, what I'm going to do is I'm going to group my terms into pairs and see if there's a common factor I can pull out that way. So let's look at these two. There's no number greatest, a constant term that I can kind of pull out based off of the coefficients, but I can pull out x squared because x2 is the smallest coefficient on the variable that I see here. So if I divide the x squared out and put it outside parentheses, what am I left inside parentheses? X cubed divided by x squared is x. And x squared divided by x squared is just 1. So I'm just left with the 8 behind here. Let's look at this second pairing. I'm going to keep the negative sign here. I'm going to think of this subtraction problem as being plus a negative. So I'm just to be absolutely clear what's going on here, I'm going to have both of my values here being negative. And I'm going to look for a common factor that I can pull out. Let's see, 9 here and 72 here. 72 is divisible by 9, and they're both negative. So not only can I pull out a 9, I can pull out a negative 9. So I'm going to pull out a negative 9 here. And then what's left inside parentheses? Well, I didn't pull out any x values because 72 didn't have an x attached to it. So I'm left with just x for my first term because negative 9x divided by negative 9 just leaves me x behind. And negative 72 divided by negative 9 is positive 8. So I factored out that negative 9, and that's what I'm left with here. All right. So what I notice is that when I factored out the greatest common factor from each pair of terms, I was left behind with a common polynomial factor in both parts of this addition problem. Got a mini multiplication problem plus a mini multiplication problem, and there's a common factor there. So I'm going to pull it out again. I'm going to be left with x plus 8 as part of my multiplication problem, and the other part of my multiplication problem is going to come from that x squared minus 9. x squared minus 9. So let's not lose sight of our 0 here. I have now factored this into a multiplication problem. X squared minus 9 times, or the quantity, times x plus 8. Have I completely factored this problem? It is a multiplication problem. Can any of my factors be further broken down? X plus 8 has no kind of coefficients. It's already as simplified as it can be because it's just written in terms of x. But if I look at my x squared plus 9, that pattern looks familiar. You should always carefully examine any polynomials that are not first degree. The exponent is 2 or higher. Here, I have a square value as my first term and a minus a squared value of my second term. This is a difference of squares. My a value must be x, because x squared gives us x squared. And my b value must be 3, because 3 squared gives us 9. Therefore, I can factor this one more time. I can write x squared minus 9 as being x plus 3 times x minus 3. And then, of course, I can't forget about that x plus 8 that we had before. So don't lose track of the factors that you've already determined. This is now the fully factored form. And we can use the zero product property to find out what the possible values of x are. So either x plus 3 equals 0, or x minus 3 equals 0, or x plus 8 equals 0. Solving each of those equations, I subtract 3 from both sides and get x equals negative 3. I add 3 to both sides and get that x equals positive 3. I subtract 8 from both sides and get that x equals negative 8. So I've determined the math roots of this polynomial. Mathematically, all of these are solutions. But this was a word problem, so let's check to see which solution or solutions make sense. It says find the dimensions of the piece of equipment. I want these to be like length and width measurements. Negative measurements here don't make sense. Only positive measurements make sense. So x equals positive 3 makes sense. And then I can figure out my length, my width, and my height by following these. The length is x meters. Well, that's 3. My width is x minus 1. So that's 3 minus 1, which is 2 meters. And my height is x plus 9. So 3 plus 9, which is 12 meters. So now I know the dimensions of my container, and we finished the problem. I hope this helped.